numbers of the universe boggle the human mind.
In the observable part of the universe, there's something like 100 billion galaxies, each with billions of stars.
The Andromeda Galaxy is about 2.5 million light years away.
The Earth is orbiting the Sun at a speed of about 66,000 miles per hour.
Most of us give up even trying to comprehend such titanic sizes, distances, and speeds. But are there ways to bring the sweep of the cosmos down to Earth? To help us understand how big, how far, and how fast. Planet Earth, for all its wide expanses, deep seas, and massive mountains, amounts to a speck of dust when stacked up against the immensity of the cosmos.
The observable universe contains of order 100 billion galaxies, and then each galaxy, like the Milky Way, contains of order 100 billion stars.
The numbers quickly get up into the millions, and then the billions, and even the trillions, and by then we've really lost all sense of what that really means.
The human mind is finely tuned to deal with the scale of day-to-day experience. The brain can understand traveling 50 miles in a day, but what about 500,000? And a person may know what it's like to move at 100 miles per hour. But what about 100 million?
Numbers like millions and billions and certainly trillions are very hard for most people to imagine because, frankly, most of us don't have billions or trillions of anything.
So how can we ever know the universe if our brains can't really comprehend its massive scale?
Doing scale models of objects in the universe is really helpful because it brings them down to sizes that we can imagine, that we do see in our normal everyday lives.
We can start by cutting the biggest players of the night sky, planets, stars, and galaxies, down to an earthly scale. There are two ways to evaluate size. We can measure dimensions, meaning height, length, and width, or calculate bulk, also known as mass. Bigger doesn't always mean more massive.
Let's say a balloon has the same volume as a bowling ball, but the bowling ball has more mass because it's denser. It's just got more mass crammed into that same volume.
To help get a grasp on some of the immense masses floating around our universe, astronomer Laura Danley visits a monster truck rally. A place where objects of hugely differing masses often collide.
We've got everything from a small toy truck to the giant monster truck. And that gives us a range of mass that will help us understand how massive things are in our solar system compared to each other and how massive our own sun is compared to some other stars.
We begin the comparison with Jupiter, known as the king of planets, and for good reason. Its mass amounts to more than 4 octillion pounds. That's a 4, followed by 27 zeros. Put another way, it would take more than 300 Earths to match Jupiter's mass. But even that is measly when compared to the Sun.
The Sun is by far the most massive thing in our solar system. It's about 1,000 times more massive than Jupiter, the biggest planet. Well, by comparison, this car behind me is about 3,000 pounds, and this little toy truck is about 3 pounds. So that's about the same difference between the Sun and Jupiter.
It's a crushing difference, as 3,000 pounds make perfectly clear. But remember, This is a monster truck rally. And the junk car, representing our sun, may regret picking on little Jupiter.
The sun is the most massive object in our solar system, but it's not the most massive star in the galaxy. There are a lot of stars more massive than the sun.
To envision the disparity between the sun and a more massive star, let's keep the 3,000-pound junk car as the sun and put it up against a 10,000-pound monster truck, representing a star some 75 light-years away.
The difference between the monster truck and the car is about the same difference as a star called Regulus, the bright star right in the middle of Leo, about 3.5 times as massive as our sun.
3 times more massive may not seem like much. But don't forget, we're now pitting galactic giants against each other.
Well, that was quite a shock. But as you can see, 3 times the mass difference makes a difference. If we could somehow bring Regulus here and have it sit on top of the sun, that's about the same comparison.
But even monster truck-sized Regulus can't stack up to the immense mass of the true titans of the universe.
The most massive star we know orbits around the Milky Way, a little companion galaxy called the Large Magellanic Clouds, in the middle of a nebula called the Tarantula Nebula. That star has a kind of boring name, R136a, but it's still a very massive star.
R136a is a young star, about 1 million years old. Its surface temperature is 70,000 degrees, about 7 times hotter than our sun. Before 2010, stars were thought to form no bigger than 150 times the mass of the sun. But new discoveries have doubled that limit.
We think R136a is probably about 250, maybe as much as 300 times the mass of our sun.
To represent this massive star, you need a truly monstrous truck. This monster is 100 times heavier. But extreme mass also comes in small packages, where density takes the force of gravity into radical territory. The greatest massive bang for the buck we can see in the universe comes from a stellar object known as a neutron star. A neutron star is the leftover core of a supernova explosion, with its mass packed astoundingly tight.
It's got 1.5 times all of the mass of our sun crammed into a volume about 10 miles across. If you crammed one monster truck down into the size of a sugar cube, that would not be anywhere close to as dense as a neutron star. I'd need 10 million monster trucks crashed down into the size of a sugar cube.
Stack these 10 million monster truck sugar cubes 10 miles high and wide, and you've got yourself a neutron star.
Neutron stars are just bizarrely extreme objects. If you were to try to land on a neutron star, it would be absolutely impossible, because you would find that on the neutron star, you weigh about 5 billion times more than you do here on Earth.
But mass isn't everything when it comes to finding out just how big the biggest stars can be. The universe is also filled with titans that take up unimaginable amounts of space. Some of the tiny pinpricks of light we see from Earth are actually stars big enough to swallow our entire solar system. Can the human mind even comprehend the largest star in the galaxy? We're bringing the sizes, speeds, and distances of our vast universe down to a scale the human mind can comprehend. The biggest thing in our solar system by far is the Sun. In terms of sheer mass, it weighs over 300,000 times more than the Earth. But in terms of volume, it's also the solar system's physically largest object at 870,000 miles across.
So the Sun is really big compared to the Earth. It's 109 times as wide as the Earth. That actually means that over 1 million Earths could fit inside the volume of the Sun. It's really big.
But as enormous as the Sun is in earthly terms, our home star seems puny when stacked against our galaxy's lineup of stellar mammoths. With strange names taken from history and science, they push the envelope of what it means to be a star. Consider them in turn: Vega, Bellatrix, Epsilon Canis Majoris, Dubhe, Aldebaran, and finally, the super-enormous Betelgeuse and VY Canis Majoris.
Oh, wow.
Astronomer Alex Filipenko attempts to bring them down to Earth in an airplane hangar.
We're here in this airport hangar today in order to try to illustrate the relative sizes of stars, in particular big stars. We're going to inflate some balloons and even some really big weather balloons and show them in comparison with the Sun, which we've scaled down to the size of a bowling ball.
The bowling ball Sun is 8.5 inches across, which would make the Earth no bigger than a tiny bead.
My two assistants are balloon experts. They know how to inflate balloons with helium and tie them off, and they know how much to inflate them. So they're going to inflate these different balloons to different sizes.
Inflating the balloons will take us on a scaled-down tour of the Sun's big, bigger, and biggest brothers. First stop, the star Vega. Located in the constellation Lyra, Vega is one of the 5 brightest stars in the night sky. It glows blue-white because it burns hotter than our Sun.
Okay, so I've got my bowling ball Sun here. Guys, how big is this balloon?
Let's check it out. It's about 2 feet.
Right about 2 feet.
2 feet, so that's about 2.5 times the size of the bowling ball. So that's like the star Vega. It's a bluish-white star, 25 light years away, very bright star in the sky.
Next up is Bellatrix, a star in Orion, the Hunter, the brightest constellation in the sky. Well-known stars pinpoint its torso and belt. Another blue giant, Bellatrix is at Orion's right shoulder and shines 240 light years away.
So here's a bigger balloon. What's its size?
This is 4 feet.
4 feet, so that's about 5.5 times the size of my bowling ball, my Sun. So this is a bigger star. It's kind of like Bellatrix.
Bigger than Bellatrix is the hot blue star Adhara, also known as Epsilon Canis Majoris. Canis Major is a constellation whose name translates as the Great Dog.
Wow, now here's a big star, huh?
This one is 12 feet.
This thing is 17 times wider than the Sun. That's kind of like the star Epsilon Canis Majoris in the constellation Canis Major. That's the same constellation that Sirius is in. Sirius is the brightest star in the sky, but Epsilon Canis Majoris is 430 light years away. If it were at the same distance as Sirius, it would appear 15 times brighter.
Almost twice as big as Epsilon Canis Majoris is Dubhe, a giant star on the lip of the Big Dipper, 120 light years away.
Wow, cool. Well, here I see an even bigger balloon. What's its diameter?
Let's see, 21 feet.
21 feet, so that's about 30 of my bowling ball Suns. In fact, that's about the size of the star Dubhe. That star Dubhe is different from the others that we've seen. It's what's called a red giant. It's got kind of an orange color. It's cooler than the blue-white ones that we've seen previously.
Amazingly, stars come in larger sizes still. And even an airplane hangar isn't big enough to contain them. Here's where we have to place Aldebaran, a monster star known since ancient times and once thought to be a sign of riches and honor.
This balloon is about 32 feet across. Now that's roughly 45 times bigger than this bowling ball, which represents our sun. Now this balloon then is about the size of the star Aldebaran, a red giant in Taurus the Bull. It's about 65 light years away, and its true color is roughly orange.
Now even the biggest balloons fall short in representing the size of the galaxy's biggest stars. Betelgeuse, for instance, is another star in Orion. 650 light years away, it is 1,000 times the size of the sun.
Betelgeuse is so large that its radius would extend roughly to the orbit of Jupiter. So if Betelgeuse was actually in the solar system, then all the 8 planets would be completely either destroyed or totally too hot to be habitable.
But the largest known star is a beast by the name of VY Canis Majoris. By some estimates, it extends to 2,000 times the diameter of our sun.
That is a truly gargantuan star. If there were a commercial airplane flying just outside VY Canis Majoris, it would take it about 1,200 years to fully circle it.
Any object on this enormous scale seems truly alien to the human mind, an intimidating answer to the how big question about the universe. No less discomforting is how far, because distances between planets, stars, and galaxies stretch beyond all human experience.
So a really great way of bringing it home is to scale everything down to a more human scale. We're better at understanding the relative sizes of things than abstract, absolute numbers.
Take the moon. It lies a little less than 250,000 miles from Earth. You might think this isn't all that far. Well, think again.
Imagine if I shrunk the Earth down to about the size of a basketball. So if the Earth was about the size of this object here, I would actually have the moon be about the size of this tennis ball. So the next question you might ask is, given the relative sizes of these things, how far apart are they going to be from each other? To show you, I'm actually going to need some help. So Johnny is actually going to hold the Earth for me while I actually take the moon and measure out how far away it needs to be. So here goes. 1 foot, 2 feet, all the way back. We're already at 10 feet. We've got to go even more. It's already past 15. We've got to go much further. And here we are at 21 feet. That's actually how far away the moon is from the Earth in our scale model.
At 239,000 miles, the Earth-Moon distance has now become familiar to us because of Apollo missions to the moon. This is one of the few astronomical spans we can readily understand. In 6 manned moon landings, we learned that the travel time was a little more than 3 days. And the lunar commute has become a part of our collective knowledge.
Engine stop. Okay, Houston, the Challenger has landed.
But beyond the moon, the solar system extends to distances so vast. Again, our limited minds aren't really up to the task. But what would happen if we literally brought all the planets down to Earth? It can be overwhelming to consider how big, how far, and how fast everything is in our universe. Even in our solar system, the distances are almost unimaginably vast. That's why we're shrinking our solar system and bringing it down to Earth.
Imagine if we took the 870,000 miles of diameter of the sun and shrunk it down to the size of a bowling ball. What would that do to the planets? Well, we'd have to shrink them down to sizes that we have here. So we have the 8 planets of the solar system lined out, starting with Mercury all the way out to Neptune. So in this scale model, our Earth, our home, is this tiny little bead, while the sun is this bowling ball.
These bead and marble planets may be to scale with the bowling ball sun, but the distances between them aren't. To demonstrate that, physicist Clifford Johnson is going to walk the length of this miniature solar system laid out along a runway.
I have Johnny here who's going to help me measure the distances with the surveyor's wheel. Okay, so let's go and explore the solar system.
All right, let's do it.
Each foot in this scaled-down solar system represents 1 million miles in the distances between the planets.
And here we are at Mercury.
And that's 36 feet.
In reality, it's actually about 36 million miles away from the sun. It's amazing just how far this very first planet of the solar system is from the sun. So now let's go on to the second planet.
There we go.
So here we are at Venus.
And that's 67 feet.
So this bead representing Venus is about twice as far from the sun as Mercury is. It's actually, in reality, about 67 million miles away. And here we are at the Earth.
And that's 93 feet.
We have the Earth here represented by this marble, and in fact, it's in reality 93 million miles away from the sun. The way the bowling ball looks in terms of the size from here is about the size the sun appears in our sky. We have this blue bead representing the Earth, and about 2.5 inches away we have a much smaller bead representing the moon.
Remember that on a different scale, with Earth the size of a basketball, the moon was 21 feet away. To bring the whole solar system into the picture, we've had to scale down the Earth-Moon distance to mere inches.
This tiny distance between the Earth and Moon is the limit so far of manned exploration of space. Hopefully we'll do a lot better in the years to come.
On our runway, Mars orbits another 49 feet away, or almost 142 million miles from the sun. The distances beyond Mars are about to get much, much larger.
And here we are, Jupiter.
We're at 484 feet from the sun.
That's actually 3 times as far from the sun as Mars is.
With all this space between these tiny marbles, it's a wonder we can see the planets from Earth at all.
It tells us that the sun is incredibly bright, so that the light from the sun can go out to these bodies, reflect off them, and then come back to here on Earth for us to see them. Okay, onwards and outwards to Saturn.
All right, here we go.
Our 2 space explorers find Saturn 886 feet from the sun.
In fact, Saturn, at 886 million miles away from the sun, is almost twice the distance from the sun that Jupiter is from the sun. So we've come a huge extra distance, and we're not even done with the solar system yet.
At 1,800 feet, the scaled orbit of Uranus stands twice as far as Saturn, 1.8 billion miles from the sun.
I can hardly see the sun back there, and I can actually hardly see Neptune in the distance, which is our next stop on our journey. Shall we go?
Let's go.
Geez, that's far.
Yep.
And here we are, Neptune, the last of the planets.
2,798 feet from our sun.
That, from our model, translates into the real-world distance of almost 3 billion miles that Neptune is away from the sun. This far out, a planet takes a long time to do an orbit around the sun. The Neptunian year is about 165 of our Earth years. In fact, only one of those Neptunian years has passed since Neptune was actually discovered.
Viewed on this scale, it's a wonder the sun's gravity has any effect at all. And there's still more to this solar system beyond Neptune, including smaller bodies like Pluto. And then, nearly a light year away, clouds of dark, icy comets. If the space between the planets in our solar system strains human comprehension, then the vast distances between stars and galaxies totally overwhelms it. That astronomers even know how far away stars are is a mystery to Nora from Brooklyn, New York, who wants to ask the universe, how do we measure distance to stars and galaxies?
Nora, that's actually a pretty complex question. For the most nearby stars, we look at how their positions in the sky change with time as Earth orbits the sun. For more distant stars, or stars in other galaxies, we measure how bright they appear to be, compare that with their known power, and thus determine their distance.
They are distances so immense that how big and how far are questions to challenge anyone's power of comprehension. But the magnitudes of the universe also extend to speed. What scientists have discovered is that the universe is a super-velocity racetrack where even giant planets move faster than speeding bullets. We've seen how big and how far things are in space. Now we're going to see how fast. To do that, first we have to understand the celestial measuring stick known as the light year. Just like it sounds, 1 light year is the distance light travels in 1 year. That amounts to about 6 trillion miles. But that doesn't help us understand how fast light speed itself is.
The speed of light is really fast, about 186,000 miles per second. Now that's hard to conceive without an example. Imagine light were bouncing back and forth between Los Angeles and New York. It could do 38 back and forth bounces in 1 second.
In an effort to chase down the concept of the speed of light, astronomer Greg Laughlin teams with firearms expert Michael Voigt to demonstrate some of the fastest moving objects on Earth.
So the way we're going to do that is to compare the speed of light to the speed of something that's really fast here on Earth, which are bullets.
We've got a target down range, so when it hits it, you'll hear that ding on the end of it, and you kind of see how long that actually takes. This is a 204 Ruger. This is the fastest commercial cartridge on the planet right now.
We've got a 300-yard travel, so I'm really going to try to get a sense of the time that it takes for that bullet to travel down range. So let's see how that works.
Nice shot.
Boy, I couldn't get any sense. As soon as I pulled the trigger, boom, it hit the target. No sense at all of the travel time.
Because it's so difficult for the human senses to perceive the speed of these bullets, Mike sets up a highly accurate timing device known as a chronograph.
So this is the unit that the timer's actually in. Inside it's got a clock.
Okay, it looks like the chronograph's ready here.
All right. Let's put a couple rounds through here and we'll see how fast this ammo goes. And what do we have?
Wow, so that was 4,297 feet per second. So that's about 3,000 miles per hour.
Pretty quick.
Pretty quick. It's a little less than a mile per second. That's roughly 4 times the speed of sound. So, I mean, I'm impressed, but that pales in comparison to the speed of light. And the time that it took for those bullets to go from the muzzle of the gun all the way down range to hit the target, during that time, light has enough time to go all the way around the surface of the Earth from Los Angeles to Paris and then back in that same amount of time.
Moving at 670 million miles per hour, light completely demolishes any earthly experience of speed.
That really doesn't mean very much to me because the whole distance of 670 million miles is much larger than any kind of distances that we normally deal here with on Earth.
The speed of light and the speed of our world are so vastly far apart, we have to take light and slow it down to really understand the difference. For that, we go back to the speeding bullet. At 3,000 miles per hour, we can barely perceive its speed. If light moved no faster than a speeding bullet, what would happen to the world around us if we slowed it down by the same amount? For example, a commercial jet travels roughly 600 miles an hour. So, assuming the bullet represents the speed of light, how slow would the jet look?
At the scale where the speed of light is 3,000 miles per hour, then that commercial jet is crawling along so that it would take an entire minute to travel 3 inches.
An F-15 can reach Mach 2.5. That's over 1,500 miles per hour. But on this slow light scale, an F-15 needs a full minute to move 7 inches. And what about speeding bullets themselves? How slow do they look on this slow light scale?
If we go up to those high-speed rifle bullets, then they're making it just a little bit more than a foot, about 13 inches over the course of 1 minute at the scale where the 3,000 miles per hour is the actual speed of light.
In the real world, a snail moves more than twice as fast. As it turns out, much of the cosmos is zipping around at speeds we can't really comprehend.
Motion is actually the normal state of affairs in the universe. We may think we're standing still, and we are relative to the ground, but Earth is orbiting the sun is orbiting around the center of our galaxy is orbiting around in our local group of galaxies.
And all of these objects are moving at very high speeds.
The Earth is orbiting the sun at a speed of about 66,000 miles per hour. That's enough to take you around the Earth more than twice in a single hour.
Our sun is rushing around the Milky Way center at 483,000 miles per hour. And the Milky Way itself is flying through space at 1.3 million miles per hour. But the speed of light is still over 600 times faster. The simple fact remains, we live in slow motion compared to the nature of the cosmos. Modern technology doesn't travel anywhere near the speed of light.
If we travel, say, at commercial jet speed, which is 1 million times slower than the speed of light, then it's going to take us of order 4 million years to traverse that distance to the closest stars to the sun.
If it takes more years to reach the nearest star than the human race has existed, how can any person ever really understand the size of our own galaxy? By downsizing the biggest planets and stars and the velocity of light speed to the level of human experience, we can finally begin to understand some of the scales of outer space. But is there a way to do the same for the distances between the stars? Distances that utterly dwarf the human imagination? Although scientists measure the enormous distance between stars in light years, those numbers barely help us grasp the expansive nature of the galactic landscape. So let's shrink everything down to a scale where 1 light year equals 1 mile. On that scale, our sun shrinks down to the size of a sand grain.
We've calculated just how many sand grains, or how many stars, would fill our own Milky Way galaxy. And the number of stars in the Milky Way is about the same as the number of sand grains in this chest.
If you're counting, that's more than 100 billion stars. If 1 light year equals 1 mile, where is the nearest star? From the vantage point of the Griffith Observatory in Los Angeles, where astronomer Laura Danley works, the nearest sand grain would end up in Hollywood, 4 miles away. To help pinpoint sand grains positioned 4 miles apart in a dense city, we'll use mirrors to flash sunlight back and forth between them.
So Aaron and Johnny have mirrors, and they're going to reflect sunlight to help us see just how far away it is to the nearest star. So I need to get a few stars to take off to Hollywood with me. That should do. So Stan, Aaron, are you ready? You're going to be the sun staying here at Griffith Observatory. Johnny and I are headed out to Hollywood. You all set?
Let's do it.
All right, let's go.
The nearest celestial neighbor to our sun isn't a single star, but rather a grouping of 3. 2 of them, Alpha Centauri A and B, orbit each other and are about the same size as our sun. The third, Proxima Centauri, is a red dwarf star, dim and only about 10% as massive as its siblings.
I'm here on a rooftop in Hollywood, about 4 miles away from Griffith Observatory there in the background. I have in my hand a bag full of stars. I'm going to take out 3 sand grains. 1, 2, 3, throw the rest of the way, that represent our nearest stars. Proxima Centauri is actually the closest star to Earth. And on the scale of this analogy, it's about 70 feet behind me. So we'll just toss Proxima Centauri to its proper place. Alpha Centauri A and Alpha Centauri B on this scale might be about 2 feet apart, while our sun is 4 miles away at Griffith Observatory.
From here, the sand grain representing our sun will be impossible to spot. This is where the mirrors come in.
Here we are at Alpha Centauri, but now we have to find our own sun. Let's see if we can't get them to show us the sun.
Hello, Stan.
Hey, Stan. We can't see the sun. You want to send us a little sunlight our way?
Okay, sun's coming your way.
Can't see it yet. There. That was a good one. Yeah, nice and bright. Wow, look at that. That's incredible. Okay, Stan, we're going to show you the light of Alpha Centauri now.
Yes, there it is. Yep, you saw it.
They got it.
Awesome.
He sees Alpha Centauri.
In our region of the Milky Way galaxy, the typical distance between stars ranges from 3 to 5 light years. With stars the size of sand grains, we could fit about 20 in a city like Los Angeles. But if more stars crowded any closer to Earth, our cosmic neighborhood would become hazardous to life as we know it.
There's supernova going off, which would really cook the atmosphere. And if another star were to pass too close to the sun, then the planetary orbits would be badly perturbed. Planets could even be lost from the sun and sent out into interstellar space. It's really true that if we didn't have these vast amounts of real estate between the stars, we likely wouldn't even be here.
Cutting down the distance light travels in a year helps put stars in a clearer context. But can we do the same to grapple with the practically infinite dimensions of the universe itself. The Milky Way spans 100,000 light years across, and the next galaxy over is really, really far away.
The distance to the nearest galaxy like our own, the nearest spiral galaxy, the Andromeda galaxy, is about 2.5 million light years away. That's about almost 25 times the size of the Milky Way itself. So if you lined up 25 Milky Ways end on end, that would stretch to the Andromeda galaxy.
It might be clearer to scale things down some more and imagine galaxies as urban centers spread out across the United States.
Sometimes galaxies are referred to as star cities, and that's a pretty good analogy.
If we envision the Milky Way galaxy at the size of the Los Angeles metropolitan area, roughly 100 miles wide, then Andromeda would be in New York. In between would be other members of what astronomers call the local group of galaxies.
There's basically two major players in the local group. There's our galaxy, the Milky Way galaxy, and there's the Andromeda galaxy. There's another smaller spiral galaxy known as M33. And then we also have these dwarf galaxies, which contain 100 million stars, sometimes even fewer.
But even the vast distances that separate members of the local group won't be enough to save our home galaxy.
Andromeda and M33 are both headed toward the Milky Way, to the point where in a few billion years from now, they're going to have a close encounter.
On a cosmic scale, the collision seems violent. But in fact, the stars in the galaxies are so widely spaced, they will weave past each other, largely undisturbed. If humans survive that long, they'll hardly notice it here on Earth.
And a few billion years after that, they'll have merged into a single galaxy.
The Milky Way as we know it will cease to exist. Until that time comes, though, the distances between even the nearest galaxies of the local group remain beyond our grasp. And our galactic neighbors represent only a small sliver of our immense cosmos.
In the observable part of the universe, there's something like 100 billion galaxies, each with billions of stars.
If galaxies were spaced out, like urban centers throughout the United States, then to approximate the size of the observable universe, the country would have to be large enough to wrap around the Earth about 500 times. Shrinking the universe down to human scale may help us comprehend its size. But reality, of course, doesn't work that way.
The vastness of the universe sometimes makes us feel really small. We're small compared to the solar system, small compared to our galaxy, compared to the universe as a whole. But in some ways, I think we're not insignificant, because we're the only creatures we know of that have the advanced minds and curiosity and intellect to think about the universe. In a sense, we are the way in which the universe has found to know itself.
And so that must mean the universe is finally starting to figure out how awe-inspiringly vast it truly is.